Hello and welcome to this lesson in our study of integral equations. So, in this lesson, we are going to learn how to solve boundary value problems using the Green's function. Okay, we are going to solve a problem on that. So, unlike initial value problems, boundary value problems do not always have solutions. Okay, so in this lesson, I shall explain how to find solutions to boundary value problems in the cases where they exist. So the main tool I will use will be the Green's function, which was named after the English mathematician George Green, who lived from 1973 to 1841. I'm even giving you history. Okay, so I'm Wedokan Randolph, a final year student of mathematics KNUST, and I'm going to take you through this lesson. So, what is a Green's function? You know, when we have a boundary value problem and you are trying to solve it, a Green's function is constructed out of two independent solutions, y1 and y2, of the homogeneous equation. Okay, so that means that we use the Green's function to solve the homogeneous part of our differential equation with boundary conditions. So after doing that, we then build on the four properties of the Green's function to arrive at a solution to the homogeneous part. Okay, so in our previous video we discussed the four properties, but let's quickly go through them because that is what we will use to build the solution to the homogeneous part of our differential equation using a Green's function. Okay, so you know, when we have a differential equation and we are asked to use a Green's function to find the solution to it, we consider the homogeneous part and we solve that part y. So when we solve that part y, then we let our Green's function to be given as y1 and y2. In this case, let's name it j1 and j2. Okay, so that means you're always going to have a piecewise function, right? So let's say this a and this b are our endpoint, the boundary. Okay, and we have a certain epsilon here, which is the point of discontinuity. So for x less than epsilon, we have the function g1 of x, and for s greater than epsilon, we have g2 of x. So for g1 and g2 of x to be Green's function, they must satisfy these four properties. So the first property is that the operator on g of x should give us 0. In other words, the operator on g1 of x should be 0, and the operator on g2 of x should also be 0 in this range. And when we have a second order differential equation, then our operator is the second derivative. Okay. Then the second point says that J satisfy the homogeneous condition prescribed at the endpoints. So you can see that the point A and the point B are the endpoint. So at the endpoint, when it comes to the first one, g1 of x, at the endpoint you have to get 0, and for the second one too, at the endpoint, which is b, the second endpoint, we have to get 0. So that's for the second property. Don't worry, as we solve questions with that, you understand. Okay. And the third property says that J is continuous at the point of discontinuity. In other words, J of x is continuous at equals epsilon. So we have J1 of epsilon will be equal to J2 of epsilon. Then the fourth property says that the derivative of J has a discontinuity of magnitude -1 over p of x at s equals epsilon. Okay, and considering a second order differential equation, P of x is always a coefficient of y prime prime. Okay, so for the fourth property, in other words, this is what we mean. G2 prime of epsilon minus G1 prime of epsilon should be equal to negative 1 over P of epsilon. Okay, so let's take an example, and the example will let you understand what you are doing very well. So it says we should consider the boundary value problem y prime prime plus y equals negative 3 sine 2x. Then we have y of 0 to be 0 and y of pi to be what? 0. So you can see that means our endpoints are 0 and what? Pi. So we have something like this. Okay. So it says we should find the Green's function of the homogeneous part. And after that we should solve the non-homogeneous part. So with the first part of the solution, we are going to consider the homogeneous part, which is y prime prime plus y equals 0. So that's what you can see here. Then we know how to solve second order ordinary differential equations of this form. Okay, so we find the characteristic equation that will be given by r squared plus 1 equals 0. And when you solve it, you get r to be equal to plus or minus I. So since we are having complex roots, that means you're going to get cos and what? Sine. Okay. So hence the general solution for this y prime prime plus y equals 0 will be y of x to be equal to a cos x plus b sine x. Right? But if you could remember, we said that for the Green's function, we select what? Two functions, y1 and what? y2. So you could see that we have y of x equals a cos x plus b sine x here. But since we need two functions for the Green's function, like in order to use that, we take y1 to be equal to a cos x plus b sine x. Then we have to create another one, which is y2. We are calling it c cos x plus d sine x. Okay. So what this means is that we are going to have g of x, okay, to be equal to a cos x plus b sine x with s lying between 0 to t. So you could see that we started from 0, ended at pi. So we are creating a point of discontinuity here so that everything here will be J1 and everything here will be J2. So that is what we've done here. I hope you can see that. And this is the same as y1, this is the same as y2. So this here gives us our Green's function, but that's not the final solution we are looking for. What we do is that we are going to use the four properties we discussed earlier on to build our g of x, okay, like we'll get it in the final form. So the first condition is that the linear operator on g has to be what? 0. Okay, so condition 1 will always be satisfied because you can see that y is a solution to the homogeneous part. This y that we are using, this y1 and y2, is a solution to the homogeneous part. So that means condition 1 or property 1 will always be satisfied. So now we shift our focus to property 2. And that one says that there is homogeneity at the endpoint. Okay, so that means that g1 of x at x equals 0, that's will be 0, and g1 of x at x equals pi will be 0. Okay, so how do we apply that in this case? So this is where we make use of our boundary conditions. Our boundary conditions were y of 0 equals what? 0, and y prime of pi equals 0. So with our questions, sorry, there is y prime here, y prime of pi equals 0. So we take our first, no, this is y1, or this is gene1, then this is gene2. So we take gene1, and gene1 is a cos x plus b sine x. Okay, so at x equals 0, we'll get y of 0 will be equal to a cos 0 plus b sine 0. Okay, then we'll have y of 0 in a question was given to be 0. So we have 0 will be equal to a cos what? 0. Cos 0 is 1, so a times 1. Then here we'll get 0 here. So that means we'll have a to be 0. And when we take the second boundary condition and we put it inside J2, which is the same as y2. So we get y prime of x. So recall that y2 was equal to c cos x, then plus d sine x. So when we differentiate it, we get y prime of x to be equal to negative c sine x plus d cos x. Then at pi, okay, at x equals pi, we get y prime of pi will be equal to negative c sine pi plus d cos pi. Then this from the question is 0. This will give us 0. This will give us plus d cos pi is minus 1. This is the same as d equals 0. So that means we have d equals 0 here. Okay. So that means that we had a to be 0 and d to be 0. So we will come here. Then wherever you find a, we put 0 there. Wherever you find d, we put 0 there. So that will give us this. So that means after applying the second property, now our Green's function has been reduced to this form. Then we have to still build on it with the other two properties left. Okay. And that one says that there is continuity at x equals t. So meaning that g1 of t is equal to g2 of t. Okay. So this is g1. You can see that this here is g1 and this here is g2. So g1 of t will be b sine t and g2 of t will be c cos t. We are saying they are equal. Okay. So when we get here, we can decide to divide through by cos t and sine t. And so let me take this point here and explain why we have this. We have b sine t is equal to c cos t. When we divide through by sine t cos t, sine t cos t. So sine t cancels sine t, cos t cancels cos t. Then we get b over cos t equals to c over sine t. So as you can see here, and we are saying that we should let b over cos t is equal to c over sine t be equal to a certain alpha. Okay, a certain value, let's call it alpha. So what this means is that b over cos t is equal to alpha, and that implies that b will be equal to alpha cos t. And it also implies that c over sine t is equal to alpha, meaning c will be equal to alpha sine t. Okay, so now we have b to be alpha cos t and c to be alpha sine t. So we come back here. Wherever we find c, we put that there. Wherever we find b, we put that there. So making that substitution will give us g of x will be equal to alpha cos t sine x, then alpha sine t cos x. I hope you get that. Okay. Then the last property, property 4 says there is discontinuity at x equals t of magnitude negative 1 over p of x at x equals t. Okay. So what this means is that g2 prime of t minus g1 prime of t is equals to negative 1 over pt, where pt is the coefficient of y prime prime. So from here, this is our g1, this is our g2. So g1 of x is equal to alpha cos t sine x. When we try differentiating with respect to x, okay, we differentiate with respect to x, we will get, when you differentiate sign, you get cos. So you get alpha cos t cos x. Then at x equals t, you get j1 prime of t will be equal to alpha cos t cos t. That one will give us alpha cos square t. Then we come to g2 of x. So g2 of x is given by alpha sin t cos x. When we differentiate with respect to x, we are going to have, so when we differentiate cos, we get negative sign. So we get negative alpha sin t sin x. Then at x equals t, we get negative alpha sin t, which will give us negative alpha sine squared t. Then we come and we put it inside this relation. So we will get minus alpha sine squared t minus alpha cos squared t because negative 1 over 1. I told you p of t is the coefficient of y prime prime. In the question, it is 1. So that means we can bring minus alpha out and we get minus alpha sine squared t plus cos squared t equals negative 1. And this is a trig identity which will give us 1. So we get negative alpha times 1 will be equals negative 1. And that means we get alpha to be 1. So we come back here and we make substitution. So we'll get jx of t. We can decide to include t to it. Okay, so jx of t be equal to cos t sine x between this region and sine t cos x between that region. So this happens to be the solution to the homogeneous part. You can see that we started with a general solution. Now we are ending up with a particular solution. That's for the homogeneous part. So that was the importance of applying the Green's property. Okay, so this happens to be the solution of the homogeneous part. So now we have to solve the non-homogeneous part. That's the second part of the question. Okay, then we had negative 3 sine 2x. So when you have a differential equation and you are solving it using a Green's function, the solution is given by y of x equals integral from a to b g of xt phi of t dt, where phi of x is equal to what is here. So I'll explain to you the reason why it is that. Okay, so this is the general form of differential equation we are considering, where we have y prime prime of x plus lambda r of x y of x equals f of x. Okay, so when you decide to make y prime prime of x the subject, everything that you get is your phi of x. And with the question we are solving, we have y prime prime plus y equals negative 3 sine 2x. So looking here, that means our lambda r of x is 1. So that means we have phi of t will be equal to y of t minus what? Y of t minus f of t from the question which was given to us. So we will make substitution here. So we get y of x to be equal to integral from a to b g of xt y of t minus f of t dt. When we expand, then we get y of x to be equal to integral from a to b g of xt y of t dt minus integral from a to b g of xt f of t dt. And this happens to be the solution for the homogeneous part. So that means solving the non-homogeneous part, you're interested in finding this. Okay, so that's why you can see that solution for the non-homogeneous part is given by this. And from our question, a is 0, b is pi. So we've made that substitution. But you should know that for the g of xt, we have two of them, right? And the first one, which is j1, lies between the interval 0 to x. And the second one, g2 of x, lies between the interval x to what? Pi. Okay, so when we get here, we know that from the question, our J1 of xt is equal to cos t sine x. That's from the solution we had here. Okay, so everything is from this place. Okay, so this one is J1, J2. So this is J1 and this is J2. So we have to substitute that here. Okay, so in substituting that, since our limit is from 0 to x, when we get here, we change x to t and t to x. So instead of writing cos t sine x, we write cos x sine t. Then this f of t was the non-homogeneous passing, so minus 3 sine 2t, then minus, so here too, instead of writing sine t cos x, we write sine s cos t. Then this is the non-homogeneous part, that's f of t, then the t. So we are supposed to solve this. When you multiply through, you're going to get whatever you can see here. You see, this negative will come and cancel this. The negative here will also come and cancel this. Then we have this. Okay. Then since we are integrating with respect to t, everything which contains x can be a constant. So we can bring that one out. And that will give us this when we do that. So now we have to integrate this, which will be somehow difficult to do that. So we use a trig identity for sine 2t, which is sine 2t is equal to 2 sine t cos t. So when we do that and we make substitution into this, we end up with this. Okay. And when we expand, we finally get 6 cos x integral from 0 to x cos t sine squared t dt plus 6 sine x integral from x to pi sine t cos squared t dt. Now we have to solve this and also solve this. So let's take the first part, that's this part. So we are solving the first part. So we want to solve using the substitution method. Okay, so we let u to be given by sine t. So if u is given by sine t, then du dt will be given by what? Cos t. That if you differentiate sine t, you get cos t. So making the t the subject, we get the t will be equal to du over cos t. So we'll substitute everything that we've had here. And when we do that, we get integral from 0 to x cos t times u is what? Sine t. So that means sine squared t will be u squared. Then now the t is given by what? Du cos t. So cos t will cancel cos t. And you will get integral from 0 to x u squared du. And when we integrate that, we get 1 over 3 u cubed. Then limits of integration from 0 to x. But u was given to what? Sine t. So that means we'll have 1 over 3 sine cube t from 0 to what? X. Right? Then when we put in our limit of integration, we're going to get 1 over 3 sine cube x. So that's for the first part. Now we come to the second part. So you see, we've solved the first part, so we take the second part. Yes. So with that one, we make we use substitution method to solve it. So we let v to be equal to cos t. So that means when you differentiate v, the v in the t will be given by negative sine t. Making the t the subject, we get negative dv over sine t. Then when you put it back here, we get integral from x to pi sine t, but cos t is u, so cos squared t will be v squared. Then times minus dv sine t. Sine t cancels sine t. Then we get negative x pi v squared dv. So when you integrate, you get minus v cube over 3. Limit of integration is from x to pi, but v is what? Cos t. So when you make substitution, we get this. Then when we put in our limit of integration, we get this. So evaluating it, Cos cube pi will give us negative 1. So get negative negative 1 over 3, which is 1 over 3, plus cos cube x over 3. That's for the second part. So now we make substitution. So we get 6 cos x, then this was the whole thing we evaluated. So times 1 over 3 sine cube x, then plus 6 sine x, then is the second part that we just found. So when we make simplification, this will go here 1, will go here 2. So we get 2 cos x sine cube x plus, and when we multiply 6 sine x by 1 over 3, we get 2 sine x, and 6 sine x plus cos cube x over 3 will give us 2 sine x cos cube x. So this here happens to be the solution of the non-homogeneous part. Okay, so this is how we use the Green's function to solve boundary value problems. Okay, so you can always go over, watch the video again if you didn't understand anything. Right, so thank you very much and all the best.